Hello and welcome to another live stream on the assumptions of physics. Today I thought I'd talk a little bit about essentially how physics is a little bit behind in terms of thinking and tools than math, and in particular how sort of topology and sigma algebra allow us to treat the discrete and the continuous in the same way, and how the focus should not be essentially the points, but the sets, because the sets actually correspond to propositions that are testable, so things that actually we care in physics, the things that we can verify experimentally. And the points are basically just a useful representation. So again, if we want to be more specific, pi, we never measure pi. It's sort of an abstract thing. While if something is between 3.14 and 3.15, that's something that we can actually check. And a lot of sort of modern math works with these ideas that sort of maps much better to the physics, and then allow you to understand what the mathematical detail is about, and then actually figure out that we don't have the right mathematical detail and we need to fix it. So that's more or less what I was going to talk today. I don't know if Tobias or Julius has any comments to start, but that's basically the plan.
No, not yet.
Okay, let me go and start the share so that I can write on my tablet. And yes, it should be nice. And right, so if you heard about topology, you probably know the things like that the donut, it's like the cup, right? Things like this that are not particularly helpful in understanding what topology is and why should we care. Um, and hi, Tom. And so the first thing that I think it's important, well, let's start with the formal definition of a topology. The formal definition of a topology is a set X, right, which is going to have a bunch of points. And then a topology is just a collection of subsets that contain the empty set, contain the full set, and contain all the finite intersection and arbitrary union. And of course that tells you nothing. This is a mathematical structure. Why do you want to have it? It's completely unclear. One of the things that, so the reason topology came about mathematically is sort of to generalize some things that are true in when you have distances in metric spaces, and then people realize that you don't need the full infrastructure of distances to sort of formalize these theorem. You need something less. And so one of the way that topology is described is that it sort of defines what continuity is. That the problem is that then you define continuity in terms of the topology, so it becomes a little bit of a circular problem. And another like hand-wavy way is that it defines a notion of closeness. And the problem with a notion of closeness is that you start thinking of a distance, but we just said before that we want to be able to do things without a distance, so the notion of closeness, it's not really the best way either. So there are basically two things that you should think. One, it's the concepts of limits and convergence. And the other is experimental verification, experimental verifiability. And it looks like these two things are disconnected, but they're actually one and the same thing. So for limits and convergence, the idea is that you have a set X and you have a sequence of points, right? And you have another point. And so you're asking whether your sequence xi is going to converge to the last point y, right? So the question is, does xi converge to y? And you can imagine that you have a function that tells you, you give it a sequence, you give it a points, and it tells you, does it converge or not. And in some sense, this function would be telling you how close points are to the other, because the sequence is going to converge to y if it becomes closer and closer to y. So you have to define this notion of closeness, how things are close to each other. And you can basically say, if I have my sequence, so imagine that this is my natural numbers, right? And the sequence, imagine of having x on this side, you're going to have a sequence of points, right? And the idea is that this sequence is going to converge to this to a point if you can find some open interval around such that after a certain n, you're always going to be inside that interval. Then at that point, you can basically say, okay, this sequence is getting close to my limit point, which you can put it here, y, and then you say that's essentially where the sequence is going to converge. And so what the open sets are basically all these intervals, these sets that you can consider as neighborhood of the point. And that's how you can then define in terms of, I give you all the open neighborhoods, I give you a sequence, and then it means that for every open neighborhood, the sequence becomes trapped by that point, by that set, and it never gets out. And the translation in terms of experimental verifiability is any of these open set becomes a statement, let's call it SI. So you can imagine that you have a sequence of statement, actually a statement S, let's put it like this, and you have your sequence x0, x1, x2, x3, right? And depending on where you are, whether you are inside the set or outside the set, then the statement is going to be false or true or false, false, true, and so on, right? And so now these become the open set, so the statements are the verifiable statements of the open set. And then you compare the truth sequence in terms of the final point y. And let's say that this is going to be true because this is a neighborhood of S. And so what you want to have that for any open set, which basically means any verifiable statement, you're going to get a sequence of false, true, false, false, right? But at the end of the day, all the statements that are true, they will become eventually true in the sequence. There is going to be some n after which all the statements are going to become true. And so this means that if you go further along in the sequence, it's like you have y, because all the statements become true, and that's it. Does this make any sense? Does this help at all? Because I'm kind of trying to play around with different way to look at this that might be a better way to introduce the subject so that then I can make a decent video about it.
Isn't that kind of we don't have any sensible truth value for points yet, but then for sets. And basically you're saying I consider, like, I define a truth value for a point by saying if at some point, or well, if you have a cutoff and then for all open neighborhoods around that point it becomes true eventually, then I assign the point a truth value. Does it make any sense?
Yeah, so the idea is that maybe that's what we should have before. Like the idea is that whenever we are measuring something, we never measure points. We always measure sets. So when we say that the mass is I don't know 4.15 kilo electrovolt plus or minus 0.005, right? Where we have an interval of confidence. This thing is a set. So anything that we do experimentally is we constrain some kind of objects within a particular set. And so that's why the sets are the primary thing. Like we never, as I said before, we never measure pi. We measure 3.14, well, 14, plus or minus 0.005. Right? That's what our measurements are. And whether the points are there or not, the points are basically there to sort of give a complete, let's say, a set from which we can take, then we can describe the sets.
Sorry if I may like try to formulate. So I suppose that the truth. Let's say that the theory. It's the absolute. There exists an absolute truth coming from the theory, which then also can still say that some value is between this and the other value. And then as we are performing experiments, we are generating this, let's say, the average with this statistical error. And in the beginning, when our apparatus is, not so efficient, we have these intervals which are, larger, partially overlapping with this, actual truth interval, partially not. But as we get better, both the value itself stays within this absolute interval, but also the errors are also covered within this interval. And in the end, if the theory itself says that the value is bounded by plus and minus 10, and then if we say that we manage to measure the average, which is around, let's say, 0, and then the errors are, let's say, plus minus 2, then okay, with enough accuracy, now we are completely within this region. But this region was determined by the theory, or some it was an actual truth, not set by our statistical limits, but by the, I don't know, logic itself or the theory of physics itself, something like that. Is that the way to look at it?
Or even just how things are, like for example, if you shoot a ball, I don't think there is a theory that tells you exactly what the ball should be, the trajectory, and so on, right? You just go out and measure it, and you have different measurements that you can do at different times and with different precision, and each of these will be essentially a constraint of a set of possible things that you could have measured, right? So you measure the position of the sun in the sky, that there is no, like, yes, after the fact, that when you have done enough of observation, then you can predict where it is, but So that's basically the main idea, is that you can think of these abstract open sets that you have in your topology as essentially things that you can go and verify from the experimental verifiability, or the things that define the neighborhood for the convergence. And again, one of the simplifications that I'm doing right here is that the sort of the equivalence between topologies and converges of sequence is only where if the topology is second countable, if there is a countable base for the topology. But in physics, so it happens that it's always that for other reasons. And there is also a way to define convergence in topology in terms of nets and filters that generalizes that, so that everything that I say here could be translated. Instead of sequence, you put net, and everything is going to work fine. And but the point is that the way that you can also see that the convergence is really the topology is that suppose you have this function f that tells you whether xi converges to y, right? It tells you whether it's true or false. Then what you can do is you can define a closed set as one set where whenever you take a sequence of points within the set, the convergent sequence, if the sequence converges, then it always converges to a point within the set. And so if you know how convergence work, you can also define all your closed sets, and then the open sets are going to be the complement of the closed sets, and sort of everything works in the same way, which is kind of neat. And one of the things that again the stressing of sets instead of points is important because otherwise you don't understand some features, for example, between the reals and the rationals. It's a lot easier to understand their difference in terms of sets and in terms of points. And it's one of those things where people start thinking about most fundamental theories of the universe. They try to work of sets because the ideas in physics, it's always that you have a theory where you have some states, and these are the points, and then you have some other theory, and which is more precise. So now these points are some kind of approximation of these true points, and then you have another theory, and then these are the even better points, and these other points are an approximation of the other thing, and this is kind of what people have in their back of the mind a lot of the time when they do physics, and this way of looking at things just does not work as well, and one of the way to understand how things are so much better when you switch from points to sets is that if you want to characterize the real and the rational, like the standard way of the physicists have is to think as the real as just the integers, but with more points. So you take the integers and you start putting more points, and at some point you get the continuum. That's kind of unfortunately a lot of way that physicists think that how things work, and it's not true. Like if you do those procedures, you get rationals. You don't get the continuum, and so the point is both the rationals and the reals have this property that if you take any 2 points, you can always find a point in the middle, right? Both of these have these features. So if you look at the property of points, it's kind of hard to see how the reals and the rationals are different. But if you look at sets, it's a lot easier, because you can now think of the open sets. So you can take an open set from R that basically is the open sets between R to plus infinity. And you can do the same thing for your rationals. And then you can also take the open sets that go from the other side. So it's minus infinity and R and minus infinity and Q. What is true in the reals is whenever you take two of these sets and you have R1, let's say, less than R2, you can always put a point, actually less or equal, you can always put a point in the middle. So you have sets and you can always separate these two sets by a point. And in the rational, it doesn't work like that. So in the rational, you can take minus infinity and pi. That's why we like pi. And then you take the other interval, pi and plus infinity. And of course, there is no pi in the rationals. And this is where mathematicians basically say that the rationals have holes, and they're not a complete ordering because there are these points missing. And again, if you look at sets, it's very obvious to see. if you look at points, you're never going to get them. So the continuum is not just putting more points, it's the fact that these open intervals are always separated by a point. I hope that helps. So we are basically saying the sets are the things that are important, and they give us the structure that connects better to the physics, and it's sort of mathematically more interesting. But the other piece is that the sets are allow us to do generalization that would be impossible to do on the points. And this is where it's better to look at measure theory than topology. So a topology, it's if you take R, it's basically made of all sets that are open intervals or a union of open intervals. That's what the open sets become. And you get, this would be the topology, and you can get from any topology what is called a sigma algebra. And a sigma algebra, it's kind of like the topology, but it doesn't only include open sets, but it also includes closed sets and half open sets, and then basically anything that you can get through countable intersection, let's call it omega, countable union, and complement. And in terms of logical relationship, this would be an end. So you're basically testing that your tests are, two tests are both terminating with a true. So A and B are both true, S1 and S2 are both true. This corresponds to the OR, and this corresponds to the not. So basically the sigma algebra is should be thought as is the algebra of all the tests. And then when we assign probability, right, again, the way that physicists think about these type of thing is that you have a set X, you have a bunch of points, and then you have a probability function that from the point gives you a number from 0 to 1. Like, this is the naive way of thinking about this. And this does not work on the continuum, because if I have a uniform distribution, let's say between A and B, and I have a uniform distribution here, this here is a probability density. This is a probability over a length. That's the thing that it's used for, that it's uniform. And since there are infinitely many points here, right, the probability of getting each point is 0. So the probability of getting x, that x is equal to x, this is 0. And of course, I could have a uniform distribution, or I could have a triangular distribution, and this would still be true. So giving you the probability at the point absolutely tells you nothing about what the probability is, the probability distribution is. So that just does not work, right? So it's again another instances where you're thinking about the points, but the points don't matter. It's like that TV show. It's the points don't matter. So how do you actually work with this? Well, again, if you think about it physically, what you want to give the probability to, it's to the outcome of your test. Is the test going to be successful or not successful? And so the much better way conceptually is to say I have my sigma algebra, and then from which represents all the tests that I can do in that space, and then assign the probability of the test. That now becomes the chance of success of a particular test, or the chance that a statement is true. And now when you have this, then you can imagine that if I ask that the probability that x is in the interval A or B. Now this is going to be 1, and that it's the probability of X being inside A and A plus B over 2, if I have a uniform distribution, is going to be 1/2. So the probability is something that is not telling me the probability at the point, it's essentially giving me the probability of all the possible sigma algebras and all the possible intervals, and that's the primary thing. Now, in the case where your X is made of discrete elements, so for example, you have a probability distribution on the natural numbers, and because, for example, you have a die, and the die is going to be made of 6 faces, so we are on 1, 2, 3, 4, 5, 6, and then we have 1/6 in terms of probability, right? Now, in this case, yes, we can say that the probability of X being 1 is 1/6. But at this point, we can think of this one as, again, a set. So the discrete case follows essentially the same rule that we are using for the other one if we are just using sets. So the point is that now we have a tool that works the same in the continuum and in the discrete. And the same thing works for the topology as well. So if you were asking, I have a sequence of natural numbers, right, that is going to be, 0, 3, 2, 1, 3, 2, 1, 1, so on. Does it converge to 1? Well, it's only going to converge to 1 if at some point the sequence really becomes all ones. Because there is nothing close to 1. 1 is just there, it's an isolated point. And so the way that it works in the topology is that all sets in the topology are, the topology corresponds to the set of all sets. And so if you have a neighborhood of 1, well, the singleton 1 is going to be an open set that contains 1. And the only way for a sequence to be trapped by this set of one element is if the sequence itself becomes that one element. So in a sense, you have this notion of limits on discrete spaces using sets and topology that works exactly the same way in terms of definitions as it works on the continuum. And we have a notion of probability that works again in the same way in the discrete and in the continuum. And that is the way that these tools are generalized and how they work. And this is something that it falls, to me, like my experience, it falls a little bit in between the physics and the math, because typically if people are doing math, they just care that they have this machinery and they use it. And they don't really have like a motivation of why, like it just works nicely, and it does. And on the physics side, since there is no bridge of why would you care about these things, most physicists don't know why these things are there, and the motivational part is lost, and physicists still keep thinking about things in ways that were basically, let's say, 100, 150 years old. And that's just sad. So I don't know if this rambling is useful or not. I'm sort of interested to see what people think about it.
Sorry, couldn't find the button. Yeah, I think we talked about this before. To me, that makes a lot of sense, like how this cleanly generalizes like discrete or continuous into one concept. And in both cases, it works thinking about the sets. And it just becomes like too simple in the discrete case to worry about it.
Yeah.
So, I mean, in the discrete case, you wouldn't think about the singleton instead of the point that is in the singleton set, right? So you don't really care. And then in a continuous case, you just think about densities all the time, which is very nice that you can, if the measure is absolutely continuous, you can always find a probability density, but it's also not the most useful. Well, it's practical, but not for thinking about things on a fundamental level.
I don't know if there are other questions or comments. The other thing that generalizes well with these ideas are essentially notion of integrals. So one way, again, the probability, as we said before, is sort of a subset of what are called measures. So a measure, it's again a function from a sigma algebra to some real numbers. Typically, it's thought as a positive, but there are also signed measure. Once you have the positive one, you can sum a positive and a negative, and you can do these type of things. And the typical things for us that are important are notions of volume. So if you have a space X, then a notion of volume is you take a subset U and you want to say how big it is, and you want these to be additive. So if mu of U, let's call it A union B, if A and B are disjoint, you want this to just be the sum, and you also want things to work in the countable case, so that you have the union of countably many AI. Then this would be the sum of the measure of the AI. Those are basically the basic basic properties of the measure. And one of the things that you want to do typically in integration, right? You want to be able to write something that is the integral of a function of some dx, right? Some the infinitesimal displacements, and this you typically think that you have a space and you have a function f. The function f does something like this, and we are getting the area because it's like at every point we are taking a little rectangle and we're summing these up. And when you have measures, now you can essentially generalize with all this idea. So you say that you have a measure, instead of having this dx, like this interval, well, that interval is basically a measure. It's something that given a set, right? A set, again, in the sigma algebra of X is going to give you some number, a positive number, and a non-negative number. And the way that you can think about the integral is, and let's call this d mu now, because we identified that this is a measure. The way that we think about this is typically as the limit of the sum of some partitions. So you can imagine that you have a set AI, which is, they are all pairwise disjoint, and the union of the AI is the full set, and that this basically gives you a partition. Given the partition, now you can take the measure of that partition, and you can take the function at a particular small element inside there. So if this is X, you can imagine to have a partition. So this is going to be your A1, A2. In each partition, you pick a point A1, a point A2, A3, and so on. and you do the sum. So you do the sum of the value of that point multiplied by that partition. That is literally what would reduce to if you were integrating a function of the real line. And so now you have this, let's say, approximation on that partition. Now you're going to make this partition smaller in a nice way, and then you're going to be able to say that the integral is that value when you're making this partition recover, like getting small in that way. And so that way, that's basically the general way that you can generalize the notion of integral in measure theory. And again, the cool thing is that this works literally the same if you are in a discrete space. Because if you are in a discrete space, what's going to happen is that this X is going to have a natural partition in terms of the actual points, right? So you are going to get the f of x times your mu of x for a singleton, for each of singleton, which is going to be just 1. And since there is no way to refine the partition once you arrive to the singleton in a discrete space, this integral is actually the sum. So this notion of that again we do in physics, we substitute sums with integrals and so on, can be made precise. But to be able to make precise, we need to understand exactly what are the measures, what are the partitions. But once you do it, we can get all the physics that we want with our sort of hodgy-podgy, hand-wavy way, in a way that is actually precise. And wouldn't it be better so that we know exactly when it is that the sums are actually the same as the integral and when they're not? So that we know where our intuition is leading us in the right direction and when it doesn't. This actually could be even like one of the reasons I'm doing this is to think of ways to put these into videos to make to give more people as given a home moment. This is also an interesting piece. So
Have you seen this symbol with like a sum and an integral combined into one?
no,
So I've seen that in like, for example, statistical mechanics, where we have to integrate either over all of phase space,
okay,
for some partition function or something like that, or sometimes it's more like, it's a quantum mechanical system, so we have like discrete eigenstates or something like that. So we sum. And it's like, I don't really know yet, but whatever. So you write the sum symbol and then a integral symbol on top of it. And you're like, the physicist knows which to use in which case. And just whatever in that particular situation is necessary, use that one. And everybody kind of knows. Um, but what you said is like literally there is exactly one mathematical structure, a measure that literally encompasses exactly that symbol and unambiguously tells you
yeah,
what to use. And yeah, it also means like the physicist then has to by hand switch from probabilities to probability densities.
right.
I guess if I had a discrete measure, um, then I don't have a probability density. I don't know. It would be nice to
Yeah,
see in a concrete example how the units could work out.
that also kind of works out in some sense,
Hmm.
but I need to iron out some of the kinks. So let me get the question from here. Should the physics respect the Bayesian who want to know whether it should be possible for a group of people to reach an agreement on probability? Recently there was a paper by Michael. So none of this has to do with what interpretation of probability you might have. So the tools of measure theory work regardless of whether your measures represent actual distribution in terms of I have 3 particles here and 4 particles there, or It's just a process so that with a particular probability is going to give you, a chance of getting a particle here or there, or it's a credence. Like the tools are exactly the same. The only problem with Bayesianism is, again, it's one of those things that work with probability and not quite with probability densities, because there are some theorems that are slightly different, and that's the part that sort of becomes more problematic. So the whether like the probability density is exactly essentially it would become this, right? You have a ratio between a probability and the measure that basically tells you the volumes, and then whether this becomes a probability density or a probability, that becomes the problem. And if you are on a continuum, right, this, for example, mu, let's say, would have units of, let's say, length. And if you are on a discrete, this mu would actually have no units, because it's just the count. And so in this sense, and then also the value, right, becomes the correct one, in the sense that if you have this measure, then the denominator becomes smaller and smaller and smaller, and then the probability becomes smaller and smaller and smaller, because you can make these sets at a point smaller and smaller and smaller, and then you get a probability density. While if you have a discrete measure, then again you reach the smallest set, which is the set with just one element, and then you just have probability divided by 1. That's the probability of the element. So again, this you can kind of think it as you have a probability of a set and the measure of a set around U, right? And so you have sort of a sequence of UIs that in some sense goes to the singleton X, right? And you're making this limit for, let's say, UI that goes to X. Like this notation, of course, this is not how things are properly defined to make it work. But that's the idea. And so, and this is what you write, and this is called the radon, and I'm not gonna get it, this Nicodim. No, it's first the I, Nicodim. I never remember whether the I and the I and the Y are there, but it's one of the ordering. And that thing is literally the probability in the discrete and the probability density over the continuum. So even that thing works. But as we said before, there is this, the problem is the units is going to be different, but it's because the measure underneath will have different units depending on whether you are in a continuum and discrete. Technically, you can even have a measure that it's mixed, that it's on some point it's discrete and some point it's continuous, and this machinery works in the same way. In fact, any measure can be divided into 3 parts. One is that it's, let's say, continuous, that one that is that it's essentially it's non-zero at points, and the other one that it's non-zero at sets of measure 0, but that becomes a little bit more complication.
If I might give a statement, let's say, of a physicist who who knows some mathematical tricks, but is not like following the things in detail. So the physicist would say, "Oh, okay. When we have this, mixed case, why don't I just introduce, the Dirac delta function? And I know some simple rules, how to multiply by a constant, how to take Dirac delta of a function, and then all these, discrete values I just replace by, integrations over, some volume of Dirac delta, and then everything becomes, a probability density function. And then I don't need to deal with these mixtures, and I, let's say I can keep it in one picture, in this PDF picture, not like probability picture. So this would be like, the first approach that, physicists would do, because they are taught about it. That's how you deal with these, Dirac functions, which are not functions actually, as we know. But the question is like, if, when this trick applies, because this then, if it is not taught, when to use this, okay, then it becomes a problem. But I guess physical systems are usually modeled such that these issues are avoided. But then you are only limited to the problems that can be modeled like this. If you want to generalize to something different, then okay, you are lost.
Right. So Dirac functions are not functions, but they are measures. So if you have a measure, right, that it's let's say a measure of u, it's one if u contains a particular x0, and it's 0 if u does not contain a particular x0. That's exactly a Dirac measure. And in some sense, this is close to what we are doing when you are, you're making the integral of the Dirac delta function with something. You're basically measure theoretically, you're doing exactly the same thing. It's just that in some ways this is better behaved than the other. And you don't get into other mathematical problems when you're trying to do when you're trying to literally think of Dirac delta function as functions, because they're not functions, and then the other reason. As you said, like, a lot of the time there is the physics that regularize the problem so that you don't have these point mass and so on. And the reason, again, if you look at it in measure theoretically, it's because of the measure that you put down. So suppose that you have a state space X, right? And even statistical mechanics, you will want to have a measure that tells you how many states are there. How many states in U, right? This is the Liouville measure that you have in classical mechanics, for example. This is the thing that you want to have in physics, because whenever you want to make a row that it's a probability density, you will want to have the probability density in terms of states. You will want to have this to have probability over number of states. Because when you're going to calculate your entropy, for example, you will need this in these units, because the physical entropy is going to be the entropy of the distribution when you're counting things in terms of states, right? And once you realize that that's what you want physically, now imagine that you have a probability on a set U that is different than 0, right? It's greater than 0. So you have a probability that the system is inside the set U, or that you're going to produce something in the set U, and so on. Now, if you said, well, the number of states that I have in U is 0, that would make no sense. Because on one side you're saying, oh yes, the state has the system has a probability, finite probability to be in the set, but there are no states there. That does not make any sense, right? So it has to be that this, if the probability is non-zero, then there has to be non-zero number of states associated to that probability. This means, in the language of measure theory, that P is absolutely continuous to mu, and therefore that the derivative, the random negative derivative that we saw before, this always exists, and it's well formed, so that your probability density always exists. So the mathematical requirements for probability density to always exist, so that you don't have your Dirac deltas and other weird thing, is that whenever you have a probability that is non-zero in a set, you better have some states in that set, which of course physically makes sense. So So instead of just saying, oh yeah, but in physics is everything will be behaved, so I'm not gonna care about. If you look at this closely, you say, well, actually there is a physical reason why things are well behaved in physics, and now I know, why things work in some sense. Of course, this is not gonna change anything that you do when you're trying to make the calculation. It just validates the intuition of the physicist. But now the physicist and the mathematician can understand why we have some mathematical structure and why the physics actually constrains us to mathematical structure that are reasonable. And we are okay by sort of removing the other case because the case where this is not valid is not physically interesting or physically possible.
So then maybe a question is, maybe it's more like, I don't know, it's a philosophical question. So of course we see around us the world, and we see various processes, and we can model them mathematically, and we know what to, let's say when we build a model for processes around us, we know what to expect because we see it in real life. But when we are trying to, I don't know, let's say, perform experiment on in some domain, in energy momentum scale, whatever, and we have no idea what to expect, and we're building a model. And if we don't have this deeper, understanding, then we would keep applying the tools that we know that worked for the natural world, the world around us. But then the question is, at some point, you like, if the world, let's say this quantum world you're trying to explore is not working according to this standard intuition, then it might be that we have to relax some of these assumptions which make the machinery break, which previously worked fine for classical processes. But how to know when to do what? Well, that's you could do this, enumerate, first, try relax first condition, try relax second condition, but one has to know these conditions. If you don't know the conditions, then you just keep applying the wrong tools, and then you get bad intuition, and then you might get stuck.
Yeah, and I think that's exactly what's happening right now in the foundation, that you don't know exactly why you have the tools, why you're using them, what's their realm of applicability, and sometimes mathematicians generalize to things that are clearly not what the physicist will ever need. So the topology is a good example. As I said before, we are only interested in topology that are set of countable, where everything is fully defined by countable sequences. And the reason is because in physics we are limited by the number of tests that we can do. And so the way that we can approach and we can do limits is only with countable sequences. We can't do anything else. Or in another way is since we can only, at every finite time we can only run finitely many tests, the only limit that we're going to have is to extend those finitely many tests to a countable infinity by allowing us an arbitrary amount of time. And that's it. So we're never going to be able to do more than that. So any topology that it's not fully defined by countable sequences is not something that in physics we can reach. And so a lot of things that are done in set theory with more abstract constructions and so on that cannot possibly have a characterization in terms of a second countable topological space in terms of sequences becomes things that are too general in some sense to be useful to a physicist. And so it's only by going through all these details in the math and understanding which one are physically motivated and which one are specific in some circumstances that you can know how to generalize. And I don't think this can be done. Like I think a lot of stuff in beyond the standard model, quantum gravity and so on is not going to work. It's just people spinning their wheel because they haven't done the due diligence, so they don't know what can be generalized and what cannot.
So I understand that then there is this issue or this tension that on one hand we have time only to perform finite number of measurements. But if we take this as, let's say, if we strictly follow this and we build a mathematical model which only allows finite number of measurements, then our theories would be extremely, how to say. They are continuous but not differentiable. Yes, at each point we have a jump in value, and this would be so difficult to work with. So of course, to make the mathematics easier, we then switch to to continuous models or differentiable models. Better say differential models, which then are easy, more tractable in computations. But then this is not what we can measure, because we cannot measure what exactly happens at every single point in space and time. So then we need to find some, I don't know, is it philosophical, is it like societal decision, but we have to decide how we bridge between finite number of tests with mathematically tractable calculations.
No, the infinite versus finite is actually not just a matter of convenience. It's like you get different models. So if we had no use for infinities, then the world would be a lot simpler. And more than infinities, what is actually important is the infinitesimal, is the fact that you can always make these interval smaller and smaller and smaller, right? If you don't have that, if you didn't have that, if everything would become discrete at some point, none of these tools would be useful, and they wouldn't match the actual experiment. Oh, there was a comment before. Does a hypothetical probability of value of 2 means a violation of law of contradiction? So all the sigma algebra relies on the fact that you have the complement, that you have the negation. So all of this assumes law of excluded middle. It's standard classical logic. So going back to the discrete versus continuum. So it's again one of those things that you understand better as sets instead of points. So the issue of why you need the continuum is because these sets that represent your proposition are never like this. Like they're not like this. Like that you have a set, and then you have another set which is exactly after it, and then another set. Like the propositions that we have are not of this type. The fact that you have the continuum is because you can always have overlaps. And overlaps of these, and overlaps of these, and overlaps, right? That's what gives you the infinity and the continuum, and that is why we can't just say we just have discrete set of points and everything is finite math and everything works fine. Because the way that these propositions are not always reducible to a set of, let's say, a finite set of mutually exclusive cases. And this is true even in quantum mechanics. In quantum mechanics, if you imagine that your block ball as being your two-state systems and all your pure states are points on a ball, whenever you say I have these states, right, you are going to be identifying, let's say, a small region here, and you're saying my state is in there. But if you were discrete, right, you would have 2 points, and you would be able to say I have this state or I have this state, and so you always identify a single element when you make your statement and your experimental verification. But in quantum mechanics, you can't. When you say spin up, you never say. It's not that you measure the point. You measure spin up to some tolerance. And so again, what's going to happen is that even if you have the system is a quantum system, is quantized, it's still on the continuum. It's not discrete. This is one of the things that, again, it's people get very, very confused by quantum mechanics. Quantum mechanics is not discrete. It's still on the continuum. And when you're making a movement in quantum mechanics, you're making like a nice rotation on the ball. It's a continuous motion in time. If the space would be discrete, the only way that you can evolve would be through jumps. And that's not at all what quantum mechanics does. So if a door is in superposition of being closed and open, it is not in both states. So again, quantum mechanics, this is up and this is down. Let's say z plus and z down, z plus and z minus. The fact that it's in a superposition, you're just in any point, in any other point on the surface. This is just C1 Z up plus C2 Z down. And the probability there is just you take the vertical line, you take a plane that intersect with this point, and the probability of getting Z is the vertical distance between here and here. So if this is 1 and this is 0, this distance is the probability of getting Z plus given psi. Again, this is all can be done measured theoretically. It becomes a little bit more complicated because you need to define other things, but there is nothing, there is no contradiction. It's just another state. If you extend the probability measure by 2, you can always take a probability measure and multiply it by a constant. It doesn't really do anything. Probability measure are normalized to 1 because 1 is true and 0 is false by convention. You could normalize it to 100 and then you say 50%, right? That 50 is because you chose a different normalization constant. It doesn't change. Okay, so these are kind of the things that I feel that any physicist that want to know and work on foundations, should have clear in their head, and I don't think they are being told or taught and whatnot, and I have no idea how to sort of communicate what should be done. I don't know. I just see the vast majority of people that work in foundation that have no sense of these things mathematically, or people on the math that have no sense of what is the physical importance of any of this. And I know that the gap needs to be bridged, and I have no idea how that should be done. So if somebody has an idea of what should be done, please let me know. I have no real idea for next time. If somebody wants to propose something, do let me know. Otherwise, it's already been an hour. If there are no other questions, we can stop. Okay, let's stop it here then. Thank everybody, and see you next week.
Bye. See ya.